Hello everyone, let's get started with section 3.4 in calculus. It will feel somewhat similar to 3.3. It's kind of dealing with something slightly different. It's concavity and the second derivative test. In 3.3, we mainly dealt with how knowing whether a function is increasing or decreasing and how it's useful. But in 3.4, we get to start looking at how the derivative of the function is increasing or decreasing and what that can provide for us. Anyway, when the derivative is increasing or decreasing, it talks about the actual curvature of the function itself, which is referred to as concavity. So the definition of concavity is below. If the graph of the original function is concave upward, when the derivative is increasing, and it's concave downward, which we'll call concave down, and concave up, respectively, when the derivative is decreasing. Concavity can also be looked at visually. If the tangent line touches the point but remains above the function, you're concave down. If it's below the function, you're concave up. Now, what we remember is to find where the function was increasing or decreasing, we had to take the derivative of the function. So to find out where the derivative is increasing or decreasing, we have to take the derivative of the derivative, which is really the second derivative. So down below is a little definition of what the test for concavity is. If f is a function whose second derivative exists on an interval, when the second derivative is positive, then the graph is concave upward. When the second derivative is negative, it's concave downward. And to separate and test for this, much like we did with the first derivative test, you're going to take the second derivative, find out where it's 0 or undefined, and separate your functions into intervals. It's in order to determine positive being concave up, negative being concave down, and we'll have a special way we talk about the critical values of the second derivative after we do this one time. So, find the open intervals over which the function f of x equals 6 over x squared plus 3 is concave up and concave down. So again, this requires the second derivative. I'm going to rewrite the function as 6 times x squared plus 3 to the negative first power. This is going to require a chain rule to take the derivative. So we have 6 times negative 1 times x squared plus 3 to the negative second times the derivative of the inside with the chain rule, 2x. And all of this should be 6 times negative 1 times 2x is negative 12x over x squared plus 3 squared. Unfortunately, that's just the first derivative, so I need the second derivative, which will require quotient rule from here, or product rule if you leave it to the negative second power. We'll go ahead and do the quotient rule. So low x squared plus 3 squared times the derivative of the numerator minus the numerator times the derivative of the denominator, which is going to be chain rule. So that will be 2 times x squared plus 3 to the first times 2x all over x squared plus 3 squared squared, which is to the fourth. So this is negative 12 times x squared plus 3 squared minus, if I look at this, we've got 2 times 2x, which is 4x, times negative 12x, so it's negative 48x, but it's a minus, so it'll be plus 48x times x squared plus 3 all over x squared plus 3 to the fourth. And there's x squared plus 3's that can cancel. So we'll have negative 12 times x squared plus 3 plus 48x over x squared plus 3 to the fourth, or to the third, no, because we removed an x squared plus 3. Oh, sorry, this is 48x squared, excuse me here. And from here, we see that if I distributed the negative 12, we would get negative 12x squared plus 48x squared would make 36x squared. Negative 12 times 3 minus 36 over x squared plus 3 cubed. And what we really have to do is find out where these are 0 and find out which in a fraction, as we remember, what part of the fraction determines whether or not the whole fraction is 0? It's actually the numerator. So when you have ones like this, the denominator determines where it's undefined, but the numerator is the one that determines where it's 0. So we really can set the numerator equal to 0 and the denominator equal to 0 to find all of our potential critical values. So in our case though, when is 36x squared minus 36 equal to 0? Factoring out the 36, that's x squared minus 1, which means when is x squared minus 1 0? When x is plus or minus 1. In the denominator, because it's a positive, x squared, or a non-negative, plus 3, this will always be positive, so it doesn't produce any values. So when we do our chart, our critical values are negative 1 and 1. What we would like to do is use our positives and negatives by plugging in values, much like our first derivative test, to determine whether things are positive or negative. We'll pick negative 2, 0, and 2. And again, I'm going to plug them into the second derivative just to see. Now we know the denominator is always positive, so it's really about whether the numerator is positive or not. If we plug in negative 2, 36x squared minus 36 will be positive because negative 2 squared will be bigger than 1. So this will be positive over positive, which is positive. Plugging in 0, it'll be 0 minus 36, so this is negative over positive, which is negative. And 2 will be similar to negative 2, positive over positive, which is positive. So what we can say is that it's concave up anywhere where it's positive, which would be from negative infinity to negative 1, and from 1 to infinity, and it's concave down just in the middle there between negative 1 and 1. So this will feel very, very similar to the way we do the first derivative test, determining increasing and decreasing. But in the first derivative test, usually we also determined if those critical points were maximums or minimums. So we need to have a way of talking about the transitions between concave up and concave down at these critical points, negative 1 and 1, and these are referred to as points of inflection. They're not differentiated between like the relative extreme are, the maximums and minimums. We just generally call them all points of inflection. So down below is a definition, but generally you have a point of inflection if the concavity is changing from upward to downward or downward to upward. And again, much like relative extrema, you can only have points of inflection when the second derivative is equal to 0 or it doesn't exist. And we'll continue with 3.4 in the next video.